In this slide, we'll study the steady state response of a sinusoid. This is the input that we are given, and over here we're given a difference equation. Y of n is the output and x of n is the input, and this whole equation is called a difference equation. We'll understand more about difference equation later, but now all you need to understand is that we are going to use the shifting property of the Fourier transform. Basically, we have x of n that can be Fourier transformed to x of omega, and x of n minus m, a delayed version of x of n, is actually only given by x of omega times e minus j omega m. So this delay causes this extra notation or expression to form outside x of omega. And we are going to take Fourier transform of this equation, and this is what we're going to do. Y of n becomes y of omega minus 0.9 y of omega, and that single delay becomes e minus j omega times 1 because it is only delayed by one sample. And the next one is plus 0.36 y of omega e minus j omega multiplied by 2. So we basically use the shifting property and we just convert this difference equation into its Fourier transform domain, and we use the extra e minus j omega m to denote the delayed version of this expression over here. You can then immediately see that we can collect y of omega, and then we will be left with this expression in the bottom. So what we basically have done is that we have taken this expression and we have also done it for the right hand side for x of omega, because x of omega is only x of omega minus 0.2 e minus j omega times x of omega, and we collect x of omega together, we have 1 minus 0.2 e minus j omega. We then form h of omega, which is typically called the frequency response, which is nothing but the Fourier transform of the impulse response, which is the output over the input. And we have this expression over here. We now have h of omega. And remember that given the input is this signal, which is actually 5 cosine some omega naught n, therefore omega naught is equals to pi over 5. All we need to do is to substitute pi over 5 into this equation, h of omega, for omega equals to pi over 5, and then we would yield the frequency response. You substitute. So the omega is here, minus j omega, minus j omega, minus 2j omega, and we will substitute. And basically all you are now doing is complex number manipulation over some division. You will get a rectangular form. You need to convert into a polar form. So this will be the magnitude and this will be the phase. So now we have a magnitude and now we have the phase. But look at this. If actually, we can take this expression h of omega and plot for 0 to pi, 0 to minus pi for h of omega, and we take the absolute, this is the absolute, and we take the phase, this is the phase. You'll see that the magnitude is an even function and the phase is an odd function. If you want to plot this and then evaluate at omega naught equals to pi over 5, what we are doing is that we are going into pi over 5 here, exactly pi over 5, and over here is minus pi over 5. We can read off the magnitude. The magnitude at the positive frequency and the negative frequency are the same, and for the phase, the positive at pi over 5, which is this some negative value here, and at the negative frequency is some positive value here. We would take the positive value at the positive frequency, this value, and use this for the phase. So finally, we see that the gain is 5 times the something, the magnitude, which is 9.9. So I guess this is about almost 1.9 if you read it carefully. And the phase, it is this expression here, minus 0.314. And if you open up and look, so if you read it off, then it will be minus 0.314. With that, we have finished this example. Thank you.